Good afternoon, everyone. Can everyone hear me okay in the back? Great. Well, welcome to Wednesday of AWS reInvent. This is SEC389. I'd like to say thanks to AWS for having me out today. I first gave this talk at Black Hat USA this year, detecting credential compromise in AWS. Is anyone out here saw my talk at Black Hat? A couple of you, great. I don't like to give the same talk twice. Those of you that saw it at Black Hat, you're going to see some of the same material, but there's a bonus at the end, in that today we're not only going to talk about how to real-time detect credential compromise in AWS, but then we're going to switch gears a little bit and talk about how can we prevent that compromise from the beginning. So if you believe, you can think about as I talk about detection on whether you believe me or not, on whether you can actually prevent compromise, prevent a credential from actually being exfilled from your instance and being used. But that's what I'm here to talk to you about today. My name is Will Binkson. I am a security engineer at Netflix. The team I'm a part of is called the Security Tools and Operations team, which shorthand is SecOps. We're not like your standard security operations team, like at most companies. We do incident response, but only when it relates to AWS. My team is a team of 6, and we're responsible for the AWS infrastructure security at Netflix. So if you think about it, our large scale, our small team is responsible for the AWS level security primitives. And I've spent the last 6 to 12 months digging deep into CloudTrail and IAM and figuring out how can we solve these problems. So today we're going to focus in the beginning about detecting compromise and how to do that quickly. And most importantly, detecting compromise from your AWS and outside of your AWS infrastructure. So we'll talk about how if an attacker took a key and used it from a different EC2 instance, how we can actually still see that. And then we're going to flip gears and talk about how to prevent it in general. So I want to first kind of set the slate and say this is not a machine learning talk. I've been corrected and said, actually, Will, this is machine learning. It's unsupervised. The machine does it. But I like to think it's not machine learning. I'm not doing these complex queries. I think it's pretty straightforward and pretty novel that when I first thought of it, I thought, wow, someone has to be doing this before. And it proved to be quite powerful. So my approach has always been, why use machine learning or like complex queries when you can take the simplistic approach and just approach it straightforward. So today is going to be a very simple talk about how to keep track of temporary tokens in your environment and then detect when they're being used outside of your AWS accounts. So the scope of this talk is the compromised AWS credentials outside of your environment. And it's important here that we emphasize the word your. When I say your, I mean your AWS infrastructure, not AWS in general. And I think this is the biggest differentiator in this method versus what you might find in AWS Guard Duty, is I am going to show you how to detect compromise outside of your AWS infrastructure, even if you took it to your rogue instance or the attacker took it to their own EC2 instance. So if you aren't familiar, the AWS Security Token Service is what is being used behind the scenes to provide credentials to your EC2 server in AWS. They're providing you the temporary credentials 1 to 6 hours lived and constantly rotating those for you on the back end in the metadata service. You might even use STS for providing developer credentials as well, depending on if you're using IAM users or not. The methods I'm going to talk about today can be used to EC2 temporary credentials and expanded to your container platforms or any other method that you want, or any other credential method that you actually want to apply it to. It's a pretty simplistic approach, and hopefully you guys will find benefit in it today. Just a quick show of hands. How many people in the crowd are security practitioners at your company? It's quite a few. Any managers? It's okay, awesome. So this should be at a high enough level and deep enough level for everyone to get something out of it today. So let's dig in. The problem we're trying to solve today is detecting the credential compromise outside of your environment. When I first started working on this, I didn't want to know if it's outside of AWS. Yes, I want to know if my developers are pulling credentials down to their laptops, but I really wanted to know, is that nation state or is that bug bounty researcher pulling credentials and actually doing something on their EC2 server? And so that's what I set out to try to solve, and I believe we've actually done this. When I looked at who was doing this, Will, I scoured the internet trying to figure out, is there anything open source that I can take advantage of? We'd been working with AWS Guard Duty for a while, and I challenged them to solve this problem. You know, AWS, you're at this source. Please help me with this. And I didn't really see anything. And I think now there are applications coming out using this method. So soon you'll see more and more things actually solving it this way. It's really hard for us, at least, at Netflix scale to solve this problem by just looking at IP addresses in our environment. If you're familiar with the Netflix environment, we're hundreds of thousands of servers across 3 regions in many, many AWS accounts. For us to understand our production environment, if we were just to poll and describe our environment in production in 3 regions, it would take us over an hour to get that data back from a describe instance call. We have to paginate, we're rate limited. So for us to keep track of the IPs in our environment, especially with how dynamic our infrastructure is, sometimes we won't actually see a server that might have been in our environment or not based on when the next polling cycle happened. So for us to have an up-to-date list of IPs is a very difficult thing to do in a polling nature. Now we've changed some of our architecture and are moving towards more of an event-driven architecture. But as I was waiting for cloud networking support on this to get an up-to-date and historic information about IPs in our environment, I came up with a solution that I'm here to present to you today. When I look at the tools that I can use to my advantage, I'm sure there's lots and lots of different things that you can use. But the main source of truth that we're going to use today is AWS CloudTrail. We're going to analyze and detect compromise using nothing but CloudTrail. And that gives us 2 powerful benefits. You can use this method historically to see if in the last 12 months have we potentially been compromised, or you can use it in real time. And as we are doing things in our environment, are any of these credential calls happening outside of our infrastructure? So AWS CloudTrail, just to recap, provides the event history in your AWS account, including action taken through the console, the CLI, SDKs, and other services, right? You can sign URLs, pass those off, and see that someone downloaded it from Chrome, from Firefox. It's very, very powerful depending on how you have it set up. There's really no excuse for anyone these days to not have CloudTrail enabled, because by default, I think it was 6 or 8 months ago, Amazon actually enabled 90 days of CloudTrail history available in the console for you. Your first CloudTrail is free of charge. The only thing you're paying for is storage. So if you think about the benefit of this audit trail for security as well as compliance and any other factors that you want to add on top, it's pretty cheap for Amazon to provide this for free. As I mentioned, you can have 90-day history in the console. I think that's available via Bodo or SDK, CLI, or you can actually just go look in the console and search there. If you were having it delivered via the simple storage service S3, you might see files being delivered in this format, this naming format. We'll talk about some of the ways that we actually have CloudTrail delivered in our accounts. You can actually have CloudTrail delivered over CloudWatch logs, which is very powerful because CloudWatch logs is a real-time CloudTrail stream versus S3 being buffered. And so if you're having S3 delivery, you're going to get a 15 to 20-minute delay and then multiple files being delivered. So you might end up in this hybrid approach of how you actually process CloudTrail with this method. But overall, you should have a pretty decent coverage once you understand CloudTrail, what's covered, what's not. And we'll talk about some tooling that we've built to actually help us understand what is actually being logged in CloudTrail. Now, if we look at a record, we're going to analyze a couple pieces of this. The user identity is very important here. And when we look at user identity in this presentation, we're going to be looking at an assumed role identity. We're going to be looking at unique session tokens for every server in your environment. This method will not only provide you information that your credential has been exfilled or potentially compromised, but it's going to tell you the actual EC2 server it was compromised from. And we'll talk about why it does that. Event source and name are pretty powerful as well. If a credential is compromised, what action was actually made and to what service within Amazon? And this is actually what we're going to key off of to start the process or that machine learning process as well. Source IP is going to be the big dollar picture here. We're going to lock to source IPs and then alert on differences from what we see. CloudTrail also provides you the request parameters and response elements, and it varies depending on which API call you actually have made, what data actually comes into CloudTrail. But the pieces that I covered here are the main pieces that you'll see every time. Now, we typically set up CloudTrail to be centrally delivered into an S3 bucket. So we have many, many accounts. We set up a single trail in every account that by default delivers into a centralized CloudTrail bucket that then is able to invoke and kick off many different pipelines within our environment. Now, we do this for multiple reasons. We can control who has access to CloudTrail this way, but it also makes it very easy to orchestrate the security measures and security tooling that we have that's triggered off CloudTrail delivery. So this is one of the recommended approaches that we always preach about is centralize your CloudTrail and fork off from there so that you can keep the data source secure as well as keep the orchestration of the number of pieces of infrastructure that process that CloudTrail to a minimum. So when we first looked at this, we wanted to understand how can we actually detect compromise. And I came up with some requirements, and I was working with our cloud network team and said, hey, I want to know all IPs in our environment across all accounts, all regions for the last hour. I want to be able to ask the question, did we have this IP at this time? And you tell me yes or no. If you think of the scale and the fact that we're so dynamic that we might miss infrastructure coming up and going away before we actually get to that problem or to that describe call, there was a problem for us. We might not actually have every IP in our environment, and this might be very noisy, depending on the number of brief calls that we've had. We've had abuse complaints come in from Amazon where we had the IP for literally 4 minutes. If you look at our history, it's pretty crazy to think of how dynamic our environment is. So this was a hard requirement that the cloud network team has been working to solve for us. If we know all IPs for the last hour, we can do this histogram sliding window analysis and say, at the time of this CloudTrail event, did we have this IP? If we had the IP, then we keep going and analyzing. And if we did not have the IP, then we alert. And we can further enrich the event and see what actually happened at that time. Was it a compromise, or was it a developer misusing a credential? As I mentioned, we're very, very large. We have to paginate almost every call we make in Amazon. The console doesn't work for some of the services in the past. As if you're familiar with our tool Spinnaker, the birth of Spinnaker was because the console didn't really work for us in the beginning. We paginate all the calls, and when we're paginating through the calls to describe our environment, we're constantly rate limited from Amazon. So it's this compounding effect of not only do we have to paginate through because we don't get all the data at once, but then we're getting rate limiting, and we're fighting our own rate limiting because we're doing these describes in production environments that are using AWS native resources as well. So lots and lots of factors working against us if we want to know all of our IPs at the same time for a history of time. And so this is where we had been trying to push Amazon to get that information for us quick. Since this wasn't going to work for us, we decided to take a new approach. And this new approach was to understand truly how AWS worked. And it wasn't until spending months in CloudTrail and understanding the data calls and what's logged and what's not, and seeing that what's in actual CloudTrail delivered over to CloudTrail logs, or CloudWatch logs, or S3 versus CloudWatch events, was I actually able to come up with this method. So understand how AWS works. Once we understand how AWS works, we're going to make a strong assumption. But I feel it's a very reasonable one. We can argue out after the fact if you'd like. But make an assumption based on how we understand things work and how typical applications work in AWS, and then profit. From these 2 points, we'll be able to tell potentially if a credential is compromised and be able to take action on that. And as I mentioned, this works both historically and real time. And if you think about the piece of information I mentioned earlier about how STS tokens work in AWS, they're anywhere from 1 to 6 hours lived on an instance. So if you went to put this in place tonight, and I'll have a link with a demo or a sample code, so you could actually go run with this if you'd like. You could go from 0 coverage to full coverage in all of your accounts in 6 hours, which I think is pretty cool. So let's take a step and see how AWS actually works. So here we have the Amazon EC2 service. We have IAM pictured here, and this is actually an IAM STS merger. We have a server, which is hosting our application, and I've shown the metadata service separate, but theoretically it's on instance local, right? It's available on the instance. We have a random AWS service that we're going to make a call to in CloudTrail. So when you deploy a service in AWS and you're actually attaching a role to it, the Amazon EC2 service is going to perform an assume role to the STS service. it's going to get credentials from the IAM service and pass those back to Amazon EC2. Amazon EC2 is then going to pass these credentials to the metadata service, and that's going to be made available to your application and any process running on your box by default at the metadata endpoint URL. I'm sure every security practitioner in here is familiar with that URL. It could be the most powerful thing in our existence, and also one of the most scary things when a bug bounty researcher includes it in his write-up to you. The SDKers or applications are going to reach out to the metadata service to get credentials. They will use those credentials to sign and craft calls and make a call to the AWS service. And then the AWS service is actually the one that's going to write the CloudTrail log. And that's an important piece because CloudTrail within AWS is a service for other AWS services. They don't mandate what's logged. They provide a logging service to the services, and it's up to the service to understand or to actually log the calls. So if you think something should be logged, you should complain to the service team, not the CloudTrail team, because the CloudTrail is just a mechanism for teams to log things. And that's an understanding that you should have if you're ever looking at CloudTrail and wonder why something isn't logged or not. By default, most management calls are logged. Data events are logged depending on whether the service is supported in CloudTrail or not. So having this understanding of how AWS works, the most important piece here is that the assume role call from the EC2 service is actually delivered in CloudTrail. It's not hidden. It's delivered in the CloudTrail or CloudWatch logs version of the trail, as well as the S3 delivered version of the trail. However, it's not delivered over CloudWatch event CloudTrail delivery. So you still, if you want to do everything off of events, you're going to need a hybrid approach. And the demo I'm going to show you today is off of CloudWatch events. But it's very, very powerful and full coverage if done correctly. So now that we have an understanding of how AWS actually works, as far as credentials for your EC2 server, the strong assumption that we're going to make, if you remember I said the IP is the moneymaker here. The strong assumption that we're going to make here is first call wins. So the first IP that we see from a temporary credential once it's been created is the IP that we're actually going to lock to. And every subsequent call that's logged from that temporary credential is going to be analyzed against that lock IP. And if they differ, then we'll alert. Now, this is an eye chart. I'm going to walk you through this with a magnification. Should be pretty clear. But we're going to walk through this flow chart. The pink icons here represent path to compromise or detection. So we'll walk through this quickly. We'll then go through a manual exploration of CloudTrail, hop into a real-time demo, and then we'll move into the prevention. So if we wanted to actually detect, we're going to process CloudTrail events as they happen. So a CloudTrail file is delivered with multiple records, and we're going to loop through and look at these records. The first thing that we're going to look for is the EC2 assume role call to actually create that temporary token to pass to the metadata service. That's going to create the initial data source for our detection. If we don't have that temporary credential, we're going to add it to the Dynamo table, and we're going to utilize Dynamo TTL features in order to keep our data source not stale and allow Dynamo to just clean up our table for us. So even as servers go away and that credential is no longer valid, they'll just fall off our table for us. And you don't have to actually monitor or prune that Dynamo table yourself. So the first time we see a temporary credential being crafted, we'll add it to the table. Every other time that we see EC2 assume role, we're going to just update the table and extend that TTL value. If your server's still running, the EC2 service is going to continue to assume that role and pass new credentials to your metadata service. And we want to make sure that that credentials continue to be kept in the table and that TTL value stays active. Now, once we've built a table of assume roles, and these are the unique credentials per server, we're going to then look to see when they're actually used. Under user identity, you can see if it's an assume role call. If it's an assume role call, we're going to actually do a lookup and see, do we have this session in the table? If we do, then we're going to see an edge case, which I'll cover. Is it AWS making the call or an IP that we trust? If it's not, we're going to look and see, do we have a source IP logged for this? If we do, we're going to look to see if they match. If we don't, That's where we're going to lock the IP. This is the first use of that credential and where we're actually going to lock that IP source and be our comparison from that point forward. If they do match, then we're going to just continue, go back and start this loop over. If they don't match, this is where we're going to alert, and it might be a potential compromise. It might be, as I mentioned before, a developer pulling credentials down, misuse. It could be something like that, but at least we have a point to jump to and start the response phase. One important piece to know is how the source IP actually shows up in CloudTrail. So this is a simple example of what a VPC might look like with some network traffic routes. You have an internal and external subnet, you have a server in each subnet, you have an internet gateway, a NAT gateway, and VPC endpoints. So number one, you're in the external subnet, you're making a call to the internet. This is an API that isn't governed by a VPC endpoint. And so the source IP seen by Amazon is going to be the public IP of that instance. If you're internal and making a call to that same public API source, the CloudTrail is going to see the NAT gateway IP. If you're an external or internal and you made a call that you happen to have a VPC endpoint, private link, something like that in region, Amazon's going to see the private IP of that call as well as VPC information. This is important for the detection as well as the prevention of compromise that I'll cover here in the future. But you need to account for potentially seeing a private IP as a source IP as well. So if you look at the example that I'll show you the GitHub link to later, you'll see that it accounts for both a public and a private IP pair per instance as a lock to be able to accommodate VPC endpoints. So you're either going to have unique public IP for the server or the NAT gateway primarily as your IP source that you're going to see in logs. I almost did not do this reference architecture diagram because I've never drawn a diagram that was just a straight line. But I thought it further proved the point of how simple this approach can be. You literally can deliver CloudTrail to an S3 bucket, have it invoke an SNS topic so that you can have many subscribers to that CloudTrail, invoke a Lambda source, and then have your DynamoDB as your data source for this session credential to IP lock, and have a method for detecting compromise. So let's walk through this manually before we actually see a real-time demo of how this could actually work. So we start with a table with the identifier, which when EC2 actually does the first assume role, they're passing the instance ID in as the session name. And that's very interesting because that gives us the instance level attribution of detection for the compromise, as well as knowing that the instance ID is globally unique across all AWS accounts. We know that this is only ours. We're going to have a source IP, which we're initially going to leave blank. The ARN is going to be the assumed role that we're using. And this is used so that when we're actually looking in the user identity that's being used for every call. And then the TTL value, we're utilizing Dynamo's auto cleanup for us. So if we were to look at this initial CloudTrail call, we see that it's a STS assume role call. The user identity is an AWS service invoked by EC2. That's an indicator to let us know that EC2 is doing something on our behalf. But we can also tell by the source IP being ec2.amazonaws.com, as well as the user agent being ec2.amazonaws.com. When AWS services are using your credentials on your behalf, they're setting user agents and source IPs as the service domain for you so that you know that this is Amazon doing something. So here we see that this is EC2 assuming the role. We see the role session name being the instance ID here ending in 2131. And the role that they're assuming is my cool role. So if we're going to build our table, we're going to go set the identifier as the instance ID. We're going to set the ARN as my cool role and set a default TTL value of 6 hours beyond the current time. And that'll give us enough time so that when the credential expires, if the instance has gone away and it hasn't renewed, that entry is just going to fall off the Dynamo table. And we can keep our data pretty fresh. So now that we have our first entry, let's see how we actually build out that lock IP. The user identity type assumed role is what we're hinging on. Once we see this, we're going to look at the ARN. And here we see the assumed role, my cool role, of the instance ID ending in 2131. Now, in the code, we would go do a query in the Dynamo table to see if we have this session We would look to see if we have an IP and do all that. We know we just did the assume role because we just saw that trail, so let's proceed forward. We see that we're doing an EC2 describe instance call, pretty benign in US West 2. Here we see the source IP is 52.95.255.121. We do that query to the table to check to see, do we have the source IP? In this case, we don't, so we're going to go ahead and update that table, and we have our first locked temporary credential for that server itself. And so as we build this over time, we're going to have unique credentials to known source IPs built out. So within 6 hours, we'll have entire coverage across all of our infrastructure of every temporary credential minted by EC2, as well as what IPs those should come from. And now that we have an initial source of truth, we can go continue to analyze CloudTrail. We see this is type assumed role again. The ARN is assumed role my cool role of 2131. We can go down here and see that it's just an EC2 call of described volumes this time. We look at the source IP, and now we're going to take this source IP and compare it. So we go back to the table and say, okay, we have a source IP. Does it match? In this case, it does, so let's continue moving forward. If you remember that flow chart, we're just going to continue processing. If we don't have an IP or don't have that temporary credential, we're just throwing that data away temporarily. Within 6 hours, we'll have full coverage, and so it's kind of the risk that within that 6-hour window that you start that you might throw away a compromised call, but within 6 hours, you're going to have full coverage. So as we analyze next, we're going to continue to do the same thing. It's an assumed role call of my cool role ending in 2131. We know this is what we're doing. Event source is STS get caller identity. That could be suspicious in itself. It's kind of like the who am I call of Linux. It's going to return the actual identity of the credential that you're using. The one benefit to that is it's going to tell you whether it's active or not. If it's not an active credential, AWS will return nothing or an error. If it is active, it'll actually tell you which credential it is and the account ID it came from. The important part here is source IP address. This appears to be an IP from San Jose, most likely my apartment, and it ends in 232. So we're going to go back to that table, do that same type of query, and say, we have an instance of 2131. We know that we have a lock IP ending in 121. We do that comparison, and then in this case, we're seeing, no, it is not the same IP, potentially compromised. Let's spin up an incident, kick off the automated pipeline, rotate credentials, whatever you want to do. So here we've actually walked through manually and detected our first potentially compromised credential from nothing. And once again, the important piece here is it's from your infrastructure, which I'll show you in the demo, is we'll not only be able to detect credentials from your laptop, but other EC2 infrastructure. So if I at Netflix were to pass a credential to my buddy at Slack and say, here, please put this in your AWS infrastructure and execute a command, I would actually detect that. So let's switch screens and actually walk through. So here I've set up an account and I have a sample service already deployed. So here we see that it ends in 34F, the instance ID. It's in the public subnet. It's running with my role, and I have a public IP of 54.209.183.1. If I switch over to the DynamoDB tab, you'll see that I have an identifier already, 34F. I filled it out with an assume role call of my role. And we already have our first call that's been made by that service with the lock IP of .183.1. And so if we were to actually go perform actions with this credential, what would that look like? So at first, I'm going to actually SSH into this box and make some calls. We're going to create an S3 bucket. So first, let me show you that the credentials are valid. We're going to call get caller identity. You can see that these credentials are for that instance, 34F. And we're going to create a bucket and call it saying that it's good from the instance in our account. So good from instance, reinvent. This is going to create a bucket. And the demo that I've set up is actually going to alert on good calls as well. So we switch over to Slack, and within 10 seconds, we're going to get an actual alert saying good call seen. We're passing the ARN back, the source and event name, and then we're seeing that the source IP matches the expected IP. This is what we expect is our environment. So what does it look like if we actually were to pull this somewhere else? So I wrote a script that will SSH into a box, curl the metadata service, steal some credentials, and pull them down. So the script looks like this. It's basically SSH in, curl that awesome endpoint, pull down the keys, export them, as well as print them, because I'm going to actually copy them and use them on a different AWS instance. So I call steal keys. There are my credentials. They're already exported, so I'm just going to go ahead and create a bucket. I'm on my laptop, not the instance. As you can tell, I didn't SSH anywhere. And so I'm going to create a bucket called from laptop, bad from laptop, reinvent. And then we'll switch over to Slack and see that the detection method actually detected it within seconds. And as I mentioned, this demo is using CloudWatch events and not the S3 delivery. So once you have sessions built via the CloudWatch logs or S3 delivery, you can then utilize CloudWatch event alerting for CloudTrail to get that real-time detection. So here we have a detection within seconds saying that the source IP ending in .92 does not match the 183.1, and so this is a potential compromise. And so this is all great. GuardDuty does this as well, but the main differentiator, I think, between this method and what GuardDuty has implemented so far is this next piece. I am now SSHing into an EC2 instance in a different account. I am going to show you that I have no credentials on this instance. I am then going to export the credentials I copied earlier, show you that these credentials are from that first instance ending in E4F, or E34F, excuse me. And now I'm going to create an S3 bucket from the other rogue account. This is mimicking an attacker, a bug bounty, a very talented individual that's been able to get your credentials. So we created a bucket bad from another AWS account. We're going to go back to Slack, and because this is recorded, I know it's going to come through. But here you can see that the source IP is an Amazon IP, and that's the important piece. We're detecting outside of your infrastructure here. And so we've detected that the IP has come from a different instance. This could even detect within your own infrastructure if you somehow, a developer has mismatched credentials and copied them from one instance to another. So it's providing you some real-time valuable information that you're having credential misuse within AWS. And it's something I'm personally very proud of and I think has been very powerful for us. So let's switch back. As we walked through this already, but we had our sample service with an IP. We built out the table. Then it locked. And then we actually did the demo. But edge cases. So I mentioned there's a few. One of them was the private IP. You have to account for your VPC endpoint calls. But also, Amazon is going to do things on your behalf. So you're going to see calls like the assumed role call that say servicename.aws or amazonaws.com. When Amazon's debugging an issue for you through support, you'll see support.amazonaws.com. If you call an API call that actually triggers Amazon to do something on your behalf, like KMS, for example, when you're restoring an encrypted snapshot, Amazon's going to make calls, and currently, right now, they put the Amazon information in there. They're working to pass your actual IP information through, but right now you have to account for potentially seeing the Amazon AWS service domain in as your source IP. So we all run in Amazon. We should trust that they're doing the right thing. So in our case, we've trusted that when we see these are calls that are valid, or you might decide to actually just note them for information. There's also potentially a case where your instance comes up and makes a call to attach an Elastic IP. Does anyone use Elastic IP in the crowd? I think everyone here does, probably. But in that case, you've had a call from your instance with its original IP, and then every subsequent call, once it actually attaches the Elastic IP, is going to be that of the new IP. So you might want to account for the associate new address types API calls, and if you see those, then within a given period of time, say a minute or two, allow one deviation from the locked IP, and then add that IP to the call. If you notice, the source IP field here is a list of strings, and that's to account for more than one potentially locked IP within your environment. The example code that I'll provide a link to at the end has this type of logic built in, so you'll be able to walk through and see how that actually works. So that was detection. Now let's flip gears and talk about, we don't want to detect, we want to prevent. Detection, as we know, could be 15 to 20 minutes. The CloudTrail or the CloudWatch events I failed to mention earlier are only mutating calls. So you notice I chose to create buckets and not list buckets or something like that, because describe calls do not come over the CloudWatch events currently. So you're only going to get real-time detection of mutating calls, but with the S3 CloudTrail or the CloudWatch log delivery, you're going to get all calls. So just something to account for. So preventing credential compromise, today we're going to focus around credentials once again, and primarily the EC2 metadata service. I'm sure we're all familiar with this IP. I should get a tattoo of it somewhere because I've dealt with this so much. I remember the first time I started playing, I had to look it up over and over, and I probably say this in my sleep now. But we're going to focus on credentials here. We're going to protect credentials and do what we call credential enforcement. Internally, we call it API protect. But we're going to try to actually enforce where API calls can actually come from. And then we're going to switch gears and talk about some new things that enable you to actually prevent credentials from being exfilled via server-side request forgery or XML external identity injection. Has anyone ever fell prey to an SSRF attack through bug bounty or other means? I won't call you out, don't worry. If you didn't raise your hand, you've yet to fall prey. At some point, I'm sure it's going to happen, be it your code or third-party code that you run. If you're not familiar with SSRF, server-side request forgery, it might look something like this. You've got a talented individual on the left making a normal web application call. That web application is actually making a remote call to a different app or service, and it's taking the response from that app and service and combining it and then providing it back to you. The talented individual sees this kind of interaction and is able to trick the application to, instead of reaching out to the remote service, reaching locally to the metadata service, most importantly to the security credential call or the security credential path, and then take those access keys back and start using them. It takes 2 calls for an attacker or talented individual to get your credential. The best part about the cloud is it's API driven. The worst part about the cloud is it's API driven. Once credentials have left your environment, depending on how privileged they are and the skill of the attacker, it might be minutes before your infrastructure is actually damaged. Does anyone run a WAF in the crowd? If you run a WAF and you've ever tried to actually prevent an attack on the metadata service, you might have done an experiment like this. In how many different IPs do I need to block the metadata path? So you go through here and see like, oh, with all these different representations of the metadata IP, I can find the metadata in many different ways. And so you blacklist these, and then you realize, oh, but how do I blacklist the bit.ly link and the Google link and all the various different short URLs that are possible? And it ends up that you can potentially detect potential SSRF, but that might end up being very noisy or things fall through. And so what we found is a WAF hasn't been very ideal for trying to prevent things like this. So we've moved towards enforcement and now this metadata protection field. So API enforcement is crafting an IAM policy to actually prevent the credentials from being valid outside of your AWS environment. And it looks something like this. And can everyone see this in the back? If not, I'll zoom in on it. I'll zoom in just in case. It's a statement that's a deny all actions on all resources. The condition composes IP blocks, VPC IDs, and VPC endpoint IDs. And it's essentially every API call that's made, the IAM service will perform these conditions for you. Does the IP address seen here fall in this block? Does it come from this VPC? Or does it come from this VPC endpoint? Now, it's important to include all 3 because there's some inconsistencies in what the services actually see depending on the call that you make. So the way that we've approached this is we're too large to have all of our IPs in here. There is a max policy size within AWS, so we're actually adding our NAT gateways. And if you remember the network flow diagram that we talked to briefly, this gives us internal coverage of roles. So one of the things, if we want to externalize a service that we try to enforce, is that the server itself should be in the internal subnet, and you should make it external via load balancer in the external subnet or some other means. And so here we've built a condition. We basically, in every account, have a unique managed policy that contains all NAT gateway IP addresses, all VPC IDs and VPC endpoint IDs. And then we go attach this to roles that are internal facing only. And when I say internal facing, I mean it's a role on a box that's deployed in the internal subnet only, no public IP. And what this has done is enabled us to actually say these IP or these calls can only come from this account. So you can take that IP and take it to my rogue instance in the EC2 and it not work. The talented individual can exfil creds via SSRF and it actually prevents compromise. And this was actually true to the case in that we had one instance of an exposed credential with bug bounty, and this API protect method made that credential null and void. He had valid credentials, but he could not do anything. And we actually challenged the researcher to be able to bypass this, and he was unable to. So this has proven very, very powerful and effective to us. But it still isn't enough, right? I mentioned it's internal only. There are needs to actually externalize boxes on the external subnet. If you do anything cross-region that's high volume, you'll understand that your NAT gateway networking price will shoot through the roof. So putting servers external is a thing, and it's definitely a thing at Netflix, so we needed to do something else. And this is where we come to metadata protection. And I've heard people, and I've bit my tongue wanting to talk about this before reInvent, where folks wanted to be able to protect the metadata service altogether. And I'm here today to tell you that you now have the power to go do this. And at the end of the talk, there will be a link to an example proxy that you can go build today and put in front of your service and protect your metadata credentials. So what we've done is we tried to work with the metadata service to have them enforce a header. If you think about any time AWS makes a major change, it can affect many customers in many different ways. So it wasn't, at least in the future, possible to what we could see that the metadata service was going to support any sort of mandatory header in the future. So I went and started making just pull requests to the individual SDKs and started setting user agents. I built an example proxy and started seeing that when SDKs in AWS were making requests to the metadata service, they were using whatever default user agent was set on the library. I'm most familiar with the Boto3 library. It uses the Python requests module. And so the user agent that the metadata service was seeing up until now was Python requests. So I started making pull requests to see, hey, could I get something done? I first started with the Ruby team. I stated my case. I had no prior knowledge of anyone on the Ruby team. They liked it. They accepted it. I took that merged pull request. I went and learned Java again. I made a pull request to Java. And I cited this as evidence that, hey, Ruby did it. Could you do it as well? And did that for multiple different languages. But the most important part is after I was able to get these teams to merge these pull requests, is I was able to get the Amazon SDK team at the global level to support never changing these for us. So from this point forward, these user agents will not change, and you can actually use these to gate access to your metadata service. So if we look at what SSRF might look like in a SDK world, now with Python, you would see when making a request to the metadata service, it would actually set a user agent Boto3 / version number / uname, all the various different user agents that you would expect. You can now put a proxy in front of the metadata service to inspect that user agent. In this case, it's something that we know is the AWS SDK, so we allow it to go through. The metadata service provides credentials back to the metadata proxy, and the proxy returns those back to the SDK, and we're off and running. So if we went back to the original SSRF example that we diagrammed, and we're running like a Python Flask app or a Django app, and we're using the Python requests module for requesting remote assets, the vulnerable app, the talented individual would trick it to trying to request the EC2 metadata service. In this case, the user agent would be the library that we're using to make requests. Since it's a Python app, I've chosen Python requests library. So the metadata proxy sees that it's not an SDK user agent, and then it just drops it on the floor and returns unauthorized, whatever you want. 401, 403, 512, get out of here. Whatever you want to return to the individual, feel free. But now that the AWS SDKs are supporting setting user agents in the SDK, you can now proxy traffic in front of your metadata service reliably, accurately, and prevent compromise in an SSRF, XXC, those classes of vulnerabilities. And so you can go deploy this across your infrastructure and mitigate an entire class. And if you think about that from a security perspective, it's very rare that you could actually go mitigate an entire class of something. And so this is something that has proven very powerful for us, and something that we're rolling out wide in our infrastructure. The supported SDKs today are the two Python libraries, Boto Core, Boto 3, the Golang library, Java version 1, and the new Java v2 library, Node.js, and Ruby. If you're using .NET, C, C++, PHP, I'm sorry. I didn't want to learn all those languages again, or set up environments, most importantly. But I believe the SDK team is making those changes to make it consistent across the board. But these are the SDKs that we actually made sure and touched today. So if you're running these languages, all you need to do is make sure that you're running an SDK within the last quarter, and you can actually use a proxy like this. The user agent strings that you might see are AWS-SDK-, typically the language name /version /uname. And then you've got the 4 Python variants. Boto Core, Boto 3, the AWS CLI is actually Python backed. So you'll see the user agent when the CLI reaches out to the metadata service to be AWS CLI. There's a new Python thing called Chalice from the Boto team. These are the user agent prefixes that you can write a proxy and make sure the user agent starts with. Now, the goal of the proxy here was to prevent these SSRF, XXC. If there's a different type of RCE on your box where the attacker is able to control headers, the server-side request forgery and XXC, the one caveat there is the talented individual, the attacker, the researcher is unable to control the header, so they can't control the user agent. So if you've given them a means to actually set the user agent, they're going to get your credential. If they're on box, they're going to curl your proxy the first time. They're going to figure it out, right? It's only a matter of time. So this means is to prevent remote attackers from actually getting your credentials. And our AppSec team has vetted it, at least the idea and the sense and how we've implemented it. And hopefully the example that we open source today proves to be very powerful for y'all, or at least kick forward something for you. One powerful thing that we've yet to do is actually start logging every path that's being hit and start trying to do anomaly detection and say, we know this application's using the Boto Core library, but all of a sudden we see the CLI user agent. That must mean someone's on box. Or this is only a Python app and we see the Java SDK. Is this some sort of new exploit tool like Paku or something that's actually running? So you can start doing a lot of really fancy things once you have this proxy and start logging and sending data forward. So we think this is going to open up a lot of really cool stuff in the security space within AWS. So some final thoughts before I open it up for about 10 minutes of Q&A. Understanding how AWS works has really made our life much, much easier. It's allowed us to easily tell whether things are false positives, develop new methodologies like this detecting credential compromise. I mentioned understanding CloudTrail and what's actually logged. As I mentioned, CloudTrail is a service within AWS, so it's up to the AWS service teams to log things. So the CloudTrail team cannot tell you what all is logged. We keep track because of a tool called RepoKid. We need to know what's logged. So we have a master list of everything that we've seen in our accounts, but we still didn't know everything. So I went out and wrote a tool called Trailblazer, which aimed to actually enumerate the API calls and then reference what was actually logged in CloudTrail to see this API call is logged as this, or this API call was made but not logged because we never saw it show up in CloudTrail. And since I did that work of actually going into the Python SDK to make these calls on demand, you can actually use Trailblazer as an attack platform as well. You can provide it a list of calls, sleeps, and regions, and Trailblazer will actually go do an automated attack. And so you can start modeling IOCs and different things and having these randomly invoked in your environment to make sure that your detections can actually detect them. There is an example Python implementation of this detection approach that I mentioned today, available in our Skunkworks repo. You can go run this on historical data, hook it up, and make the changes. Everything's in memory with this one. So if you wanted to actually go deploy it in Lambda, you need to go implement the Dynamo backend for that. But it's at least a reference piece of code to actually go play with on your CloudTrail. So hopefully you can provide that or find that very useful. And then lastly, today we flipped the switch on an example metadata proxy. It's written in Golang. It's, I think, 100 lines of Go. It's literally set up, git clone, cd into the repo, go build, and then go run the binary on your platform. It's very simplistic, very easy. It blocks traffic. You can take that as a source of truth, or you can go modify and change to your will for logging and all the various different things. But this is something that you can actually take and try out in your environment today to start protecting your metadata service. And with that, please complete your mobile surveys. And I'm open for any questions y'all have. But thank you for coming.